Well, welcome to the Structural Modeling Video Conference for December 7th, 2019. Today we were scheduled to talk about Ontology as a System version 2.0. And as I got into that specific paper and rewrite and updating it, and I found that we really needed to look at some more specific categories about ontologies and systems. And another thing that happened was that Dan Warfield set out a note that talked about the new John Warfield website that's up. And the new John Warfield website that's up has a version of the ISM Windows software on it. So we started looking at that, and there's some new opportunities there with the Windows software. There's some issues with the Windows software right now that Dan and his team is working on, and so they'll hopefully they'll kind of get that squared away soon and let everybody know what's going on. Or if I find out, I'll let everybody know. So basically, what we have on the screen now, the concepts and topics for today, essentially I kind of boiled everything down to these specific ideas. And the specific ideas are: the system is a relationship associated with a collection of objects. So we've done a lot of work in that area where we've talked about, focus really on the logical properties of a relationship. And then an ontology has relationships between and among its objects. And I distributed a paper, a chapter out of a book on ontological relationships, and also in another book that's building ontologies with basic formal ontologies, which is rather recursive, actually. It has chapter 7, which is the ontology of relations. And so again, when I was looking at these works, I found that the authors had started using the same kinds of, some of the same kinds of logical relationships in their work as we found in the AMEI. So there started to be some connections here, and I thought it would be best to actually then stop and focus and talk about this general context and these connections before we started delving into the specifics of how the logic is translated from natural language into a logic, and then the logic is translated into the computer. And what kind of value does that have, and those types of things. So let's see. So far, are there any questions about that? Okay, so I'm going to change this. I'm going to go ahead now then off of this and share a different, stop the screen share. Going to bring in a different one now, which would be this one, I believe. Okay, so now this is the more of the specifics about the discussion topics, and kind of this one focus a little bit more on the design of a language. And I think that one of the more interesting things about Warfield's work in science of generic design was the fact that there's two language types that are used in the structural modeling language, and the first one is an object language, which is used to discuss the area of interest. And then the second language is a meta language that's used to address the object language. So for systems, the object language that was proposed by Warfield was mathematics. And this specific idea, there's some very, mathematics being a formal language, has some strengths. And one of the strengths of it is you can use it to effectively and precisely engage in very large sets of data or very large systems, and use inference logic to evaluate and analyze those systems and have some confidence in the outcomes. And you can use mathematics to do that as an object language in systems to engage very large scale systems that would completely overwhelm a human being in natural language without the formalisms of the mathematics. But we need the meta language, the natural language, to actually talk about the mathematics that we're using, or the mathematics that we have put together and mathematics that we have formed into a systems language. It's not all mathematics. So the object language for, systems can incorporate many different types of formalisms, but we need to have a core piece that we can talk about. And so the idea here then is designing that specific language. And from the Science of Generic Design, it says, thus it can be presently conjectured and ultimately demonstrated that careful design of the object language, so this is careful design of the mathematical language component to structural modeling, can be augmented with natural language, serving as the meta language to produce a very powerful means of achieving high quality communication and documentation. And so this is to me, the object language and the natural language, that's what the ISM or the structural modeling software support. And they support groups of human beings in the activity of exploring large-scale systems. So we have some components here. We have the formal language, formal object language, which is mathematics, informal meta language, which is natural language, and also a careful, robust, and correct object language design. So what does that mean, right? The first thing that when you have these list of attributes, you said, well, okay, how do I know that one object language designed for systems is better, more careful, more robust, and more correct than another? So you need some characteristics that you can actually use to evaluate these languages. And they also need to support and enhance collective group intelligence and knowledge creation, and at the same time minimize resource consumption and maximize knowledge and value creation. So these are just, a few very basic types of requirements or goals, objectives, or mission functions associated with a systems language that would be implemented through group processes and procedures and augmented with software support systems.
Joe, is that your 6?
Yes, I just came up with these. Just
put them in that order.
Yeah, it just there's no real it's just kind of a small core set. I think of I'd almost call these, like mission functions or mission objectives, but this is what you kind of need to do. And then how when you start to design a system, then you'll break these down into functional requirements.
Right. But I mean, that's not a logical sequence that you have there necessarily, even though they're numbered 1 through 6.
No, it's not a logical sequence at all. It's just 6 items. Okay,
so here's something that you've got 6 items there, and we're talking in the we're talking about defining this in a natural language. I mean, we're talking in what we would call a natural language, which is spoken, I guess, is the best way of describing it in this particular format right now. And I'm not sure why it's called I mean, I suppose it's informal versus formal, formal being mathematics, informal being we create it. I mean, I'm creating my informal language, meta language as I'm speaking right now. But what about, you know, I mean, we have Helene on here, for example, who, I mean, I grew up in an English culture, and you, Joe, and Janet, and Americans grew up in and Kevin grew up in an American English culture. And Helene, of course, grew up in a French culture. And what I wonder about all of this is, when you talk about a natural language, is, you know, what comes first? And particularly when you move down to what, or not move down to, but when you go to collective group intelligence and knowledge creation, I'm just, you know, I'm concerned about that assumption. Let me put it that way.
Okay, that's really good, Peter. I think and it's right on point. So the question I would look at, and that maybe the way I would reformulate your insight, is that are there primitive fundamental concepts that are universal and available in any natural language?
Yeah.
No matter what symbols or what type of, however they're represented, these concepts then basically are put together, are represented in some way in the natural language. And so we boil that down. And so if we start looking at the idea of formal mathematics, right?
Right.
Formal mathematics doesn't change between natural language, doesn't change a natural language speaker, right?
Right.
And so fundamentally, if you anchor your systems engineering language in the formal object language of mathematics, it's anchored and is unchanged. Well, is basically stable. Doesn't matter what the type of natural language you're using to address the mathematics, because we use the meta language and natural language to talk about the mathematics. And in the AMEI, which is the logical collection of the 27 logical groups, right? What Mary and I have done is we've associated typical English language words, natural language, with those groups. But you could associate any natural language with those groups.
Just a little, to just pick up on what Peter had said. So aren't we in a big paradox or like circular references here? Because we're saying that natural languages are different. So we're focusing on the formal language, but to explain the formal language, we're going back to natural languages, which are different. So that's the thing that bothers me a little bit in this construct. And given the discussions that we've been having about literacy and systems language, etc., I'm just wondering if there isn't a need for a third component here that I don't really know the form it could have, but there's something here that feels a little bit, well, isn't there? Does it work? Well, that's my question.
It's a very good question. And of course, the dyad of the formal and informal languages came from Hilbert. So there's in the science of generic design, Warfield traces this back, all this use of the two languages, all the way back to the origins and what specifically the value, what is the value of the dyad of languages, the object language and the meta language. And so from a pure mathematics standpoint, the problem that I believe that Helena is alluding to is the fact that, and what Hilbert pointed out in that case, was that if you have a formal mathematical language, you need at least another formal mathematical language that's a meta language to talk about the object language you have. So there's nothing magic about formal or informal about object language and the meta language, because the object language and the meta language can both be formal and they are in pure mathematics. But this conflict of being able to move things apart and deal with them is essentially important. And so they did formal proofs that showed that within a formal language, right, within a formal object language, you have a closed space. So how do you talk about that? Well, you need a completely different formal language to talk about it. And so for systems engineering, which we have, which Warfield designed to have a formal object language at its core, then we have people from all walks of life that are non-mathematicians that have information that they need to talk about the formal language, right? So you use an informal piece here, and there can be gradations in the formality. But that is what the idea of when you bring people together into the observatorium, or you bring people together into a group, then they start developing a specific specialized informal language that's focused directly on their area of interest. So there are balances here. And so those are really good insights and good questions. So, but as we move forward, the idea.
Can I add one more thing? So you have,
Sure.
you have three dyads here: formal, informal, object, meta, and natural, and presumably artificial or artifactual. Robert Rosen emphasized, as did Whitehead, that the language we use for mathematics is natural language. It's human. It's a human construct that is just standardized and specialized, but so that it can be treated formally. So I think, Joe, you were just saying that the object meta distinction, those could both be formal or they could both be informal. What is useful here and what Warfield's doing is to say, let's formalize the object language, and then we will have an informal meta language. And the formal object language is just highly simplified, constrained, standardized by communities of practice who have chosen to use certain notations, terms, symbols, things like that. So I don't know if that helps, but it makes the mathematics and logic less alien if it's seen as a standardization within natural language in order to be able to treat it formally.
Yeah, that's perfect, Janet. I think that that's another way of looking at this. And so, but why would you even use formal mathematics or informal language? You could choose, right? Obviously, you can choose how these things work. And so when in these 6 things, there's 2 very general value statements. One is minimize resource consumption, and the other is maximize knowledge and value creation, right? And so I believe the real genius and insight behind the selection of the formal language and the informal language, where the formal language is the object language and the natural language is the meta language, is that by combining the 2 different types of more or less processors, one the human mind and the other computers, right, is you can carefully design a language to minimize resource consumption and carefully design an object language to maximize knowledge and value creation. So these item 5 and 6 basically are goals of the object language design and the implementation. And so those are the things I think that are important. And all of these different viewpoints are excellent. But what we need now, when you're going to select between them or select between and among them, you want to, from an engineering standpoint anyway, if you want to carefully design an object language, then you want to design it to minimize resource consumption. And you want to design it to maximize knowledge and value creation. And one of the things that we've pointed out in our analysis of the existing work is that some types of logical constructs are very, very good at minimizing resource consumption. Some of them are very good at maximizing knowledge and value creation. Other ones do not perform as well. And when we approached that insight and started looking at that, said, well, we really need a way to specifically talk about these different kinds of logical relationship groups, right? And we really need a way to actually address complexity reduction. And so what we said was fairly simple. That is, one is that uncertainty generates complexity. And there's a body of work behind that. And so what we want to do is we want to eliminate uncertainty, and we want to reduce complexity and minimize resource consumption and maximize knowledge and value creation. So one of the first things we did was we took the logical properties of reflectivity, symmetry, and transitivity, focused on those as basic components. We have put anti-symmetry aside because of the uncertainty involved. There's uncertainty involved in that. And in the specific case here, where we have people that we're getting information from, we can actually talk to the human beings and talk to the and query the information sources and resolve that uncertainty. So we do not want to take that uncertainty and put it into our formal language representation. We want to use our informal language to resolve those uncertainties to its primitive logics and then put them into the formal language. That's kind of another approach where we're saying, okay, we want to then minimize the creation of uncertainty and therefore complexity in doing that. And we use the AMEI to do that. And we also want to explore the connection between structural modeling relationships and ontology relationships. So again, as I said, Barry Smith in this chapter I sent out talks about ontological relationships, and they also talk about it in this basic formal ontology book. And we'll talk about that a little bit more in a bit. But
can I just bring back?
Sure.
To emphasize what you said there, and because hopefully that will clarify for Peter and Helene. In doing this, you need to use computation in order to gain power in your group modeling, and so that you can minimize resource use and maximize knowledge and value creation. In order to communicate with the computer, you need to get things into a formal object language. And in order to communicate with the people and have the people communicate, you need to have informal meta language. So that's where those two come from. Now, the question of whether there's a third set of primitive patterns or something, that would be in addition to the needs of the computer communication and the human communication.
Yeah, I think that's really important and a good insight, Janet. But the thing that also probably should emphasize is the fact that this is from, we're looking at the idea of formal object language and informal meta language from the document called A Science of Generic Design, okay? So this is generic type of things that will apply anywhere. But as soon as I go to a specific domain of information, then I have an existing set of formal and informal concepts, right? And
Question.
So that may be the idea, that may be the kind of the third thing that Helene may be thinking about or think might be there. And it is in any real situation where you where you use these techniques, you're going to go and apply them in a specific area that's going to have well-developed concepts. And so the formal object language and the informal components need to be applied. And they need to think, and they need to be able to incorporate these things that already exist. But you're using this mostly when you have new areas where there's changes and unknowns and uncertainty, right? So yeah, it all kind of, yeah.
Are functional requirements the only kind of requirements that you are addressing?
No, Jack, I'm actually, no, I just threw these up here just to start the discussion. This is, you know, I thought about, well, maybe I should do this in, you know, the mission requirements, functional requirements, and support requirements approach. And that became too complex to break it down that way. And I thought about some different types of ways to think about this. I said, no, I'm just going to put this small set up there and we can just talk about how these apply.
Thank you.
Yep. Yeah, I was going to use the Dahlberg approach to break it down, but then I decided not to do that either. So anyway, we just, but I think it's really important now because we have this new Windows-based software when they kind of get some of their issues squared away to look at the implementation of how people have actually implemented the interface between people and the computer. And so we really have three things now. We have the GMU ISM software that's DOS-based. And Mary and I have gone through and analyzed those, the interactions with that computer that was basically in the appendix 2 of the handbook. And then I've written structural modeling software that's web-based that reproduces those functions that were in the DOS-based system. And now there's this ISM software that's Windows-based. And it seems to be a little bit different. But, and I looked at the video, how to use it. And I think when I looked at the video, I think that was I got a much deeper insight into one of the things that Kevin has been talking about for quite a while. I think paraphrase it is that if you're bringing people together into a group collective intelligence, but if you have them rate and rank things before they have a discussion, it's not a collective activity. They're rating and ranking, and they have not had the benefit of everybody, at everybody else's knowledge. They're just putting their own individual thoughts out there. Is that kind of your view of that, Kevin?
Yeah, it's the difference. Voting is an aggregation mechanism, and the presumption is that you have individuals that have independent preferences, and there's not an interrelationship between the individual preferences. That's the basis of the utility theory. But what you find is through deliberation, and there's certain strictures about what constitutes deliberation, there becomes an interdependency of preferences by the individuals, and you also the issues that are being discussed, people determine interdependency between the issues. Voting doesn't work when you have a set of things that have interdependence. Voting is based on the idea that there's independence between what's being voted on. So yeah, so the deliberation before, well, you have the deliberation, people come to see things in a similar way. the distribution of preferences tends to converge, and an ISM is the final step in helping see the interdependency between the issues. Now, something the software doesn't do at all, and there's no version of ISM software that does this, is look at or report on the convergence of the preference, the individual preference structures, and the formation of opinion coalitions and things like that. And that's something there's a lot of work on how to do that in social network analysis, but that has not been married up with ISM yet. Anyway, going on a little.
That's okay. I appreciate it. It's really important, I think, that that these things, and so we start looking at the different aspects of the software that's available now. What I'm hoping to do, and what I would like to do, is actually once the ISM software, the Windows-based from the new John Warfield website is together, is actually work with a group of people, interested people, if anyone here is interested, and going through and doing an analysis of the functions that are being performed by that software, and then come up with a couple of tests, run a couple of tests on that software and see how it works. Specifically, run the examples given in Appendix 2 of the Handbook of Interactive Management, and there's a couple of others. And so I think this is something we talked about way early on, Kevin, is having a test bed to test software, a standard set of tests, right? And then once we have that kind of put together, then I think it's a good point, a good place to actually then re-examine and re-look at and recode basically the structural modeling web-based software that's out there, because then we have a little bit better idea of things that we really want that software to do. So with that, I'm going to then go ahead and change and look at this next, share the next screen of, look at this paper here. So ontology, ontological relations. This was kind of interesting to me. I'm not sure that I really fully understand it. The part that got my attention is back on page 228. I see we go through all this, but right here, right? Here's the part that got my attention. Figure 1, logical attributes of some formal relations, right? So we're talking about formal relations. Now, when we have, here's the transitive, the symmetrical, and the reflexive. Now, these are the ones that we use in the AMEI. Anti-symmetric we don't use because it is compound and generates complexity. And I would say we don't use it right now. There may be a case as we go forward and look at this more that we can find a place where that's useful. But right now, in every case that I've looked at it, all it does is generate more complexity. And in a ISM sense, where you have the knowledge source is all the people, you can eliminate the uncertainty associated with anti-symmetry just by asking the group. So that uncertainty should not, in my opinion, be included into the software logic. It should just ask, use empirical techniques, reduce the uncertainty, and then encode the logic at the primitive level. So that's basically what the AMEI does. And we see here what these relations that they're basically talking about. And again, part of is a relationship that we've talked about quite a bit in mereology. And it said it's transitive, symmetric, not symmetric. So it's asymmetric, but it's reflexive, right? So once we look at this, it just gives one interpretation of part of. As we pointed out before, using the AMEI, the different logical groupings, actually there are many different recorded logical versions that can be associated with part of. And using the AMEI, you can specifically identify each one. But in a group of people, when you're using it in the software and you're using it to help develop an insight into the problem at hand, there's only a few logical versions of the part of that are naturally available to people, how people naturally think about it. And so not only part of, but other types of relationships, I would suggest that we develop very simple verbal natural language tests, ask questions, question, answer with a group, so that you can pick and normalize their version of the relationship. And as this paper points out, there's other primitive types of logical relationships that need to be identified, and the identification here is basically in conflict with with what I think most people would think of in natural language. So what needs to happen here is this needs to be more well-defined, and the AMEI is the tool to do that with. And you can adjust these relationships to the specific group and then use the AMEI to translate from what the group thinks into how the group applies the logic into how the computer would apply the logic. So you would have a match up there. So there, and just my reading of this paper, there's a lot of let's see how to say this. There's lots of things that just are unanswered and confusing to me about specifically any specific applications, but I think it would be valuable to take some of these basic ontological relationships and map them through the AMEI. And then by doing that, we'll start to make a connection between ontology and ontological logic and the basic system logic and see how those match. So into this about 40 minutes now. So I'll kind of stop now and kind of open this up because I think I covered most of the general concepts. Is there any other insights, input?
Yeah, I think when Michael and I read this book, we were struck by how casual their treatment is. I think your idea is good. I think, unfortunately, this book is not, well, they do not, it's not very systematic. It's primarily designed to promote BFO. So as you see here, they don't really look at this with any precision or thoroughness. So I'm not sure what a better resource would be to do that comparison.
Yeah, so when I looked at this and went through and looked at this book and looked at the basic formal ontology, it looked like the material was generated for human computers. It was not generated to be actually translated specifically to a computer, okay, into computer logic. And their idea of ontological logic as opposed to general logic, I don't understand that, because this is supposedly the logic for this chart. This figure is a chart logic for ontological relations, which is our standard logical attributes, right? And that we used in the AMEI. So I think it's important, however, to try to use whatever mechanisms available to make it a more rigorous, so that you can go from natural language used by a group of people and then have that translated through this interface to the computer, and everybody kind of understand what's kind of going on there.
Right. Yeah, they don't really address that. They have some rules, sort of loose rules that they don't follow themselves.
Yeah,
but they don't have a clear sense of this is what the computer needs, this is what the people need, this is how you go between them.
Right. And I think this is this is the key component. And to do that, I thought, well, and it would be the subject of, the Ontology as a System version 2.0, that paper. So that's the key component right there. And it really drives, I believe, the functionality of the software, the design of the object language, and really from the science of generic design, what we're actually looking at is, how do we design an effective object language that is mathematically based and translate that effectively to natural language? And so the AMEI is a key part of that interface. And we've demonstrated that numerous times. We've gone through, we did a paper on why we don't use this anti-symmetric piece. We've done, strict order. We've talked about the ordering. We've talked about the partial ordering. Talked about all of those concepts and which ones are valuable and which ones generate complexity. And so as part of our design objectives that we want to do, right, we're going through and saying, hey, what we'd like to do is be more rigorous in this activity. And it's something that I think would be very valuable. So any other comments?
Yes, what struck me in this paper is the limitations that they list on how to use what they're talking about. And one particular one, I kind of noted some of them, but is that what they're saying is only true in virtue of the meaning of the terms involved. And what I take away from all this, and also from another paper that I read that's in the list on the Warfield website, is that there's a lot of focus that is put in the relation part or the structural part, even of the math, and less in the content and what is related to each other. And this is what I would like to address in a certain way, because to me this is where the misunderstandings, can come about, in the sense that we can have a perfect logic of assembling things, but if we're not talking about the same things, or if the way we construct the axioms that we want to chain together are different, and the content of what we're assembling is different, then there's a problem. I don't know how to formulate that exactly, but by reading all this is what came to my mind.
Well, if you would, I think you're on the right track. And if you could write that up, or just as much as you can about that, and then distribute it, I'd be more than happy, or in fact very interested in kind of contribute to some ideas about how to think about that.
Yeah, this is what I'll be focusing on. I don't know who of everyone here will be going to the IW 2020 workshop in Los Angeles at the end of January.
Mm-hmm.
But I'll be presenting something along these lines. So will you be there, Janet and Michael? Hello.
Janet
Okay.
has her mic off.
Well, anyway, so the other question I had was when you speak of standardizing natural language in order to better interact with the object language, you do this like with the people in the room. I think we already talked about this last time.
Right.
So what happens outside of the room, if I take the objective of INCOSI, for example, which is to try and come up with a system science language or some system science principles that can underpin systems engineering.
Yeah.
How does what we are doing today, or what a group is doing in terms of standardization on specific topics or on a specific domain or question, stick and get adopted at a broader industry level? Because this is what, that there's a kind of there's also a contradiction here, is that everyone is developing either open source or proprietary software or methods to make things computable. But how do you create standards where you standardize the uncertainties the same way? That's the problem, is that with people in the room, you can get a consensus on how you standardize and how you make formal clarify some uncertainties to kind of inscribe them into a formal language. But how do you get that to be adopted as a standard when the set of uncertainties becomes different every time we change the context, for example?
Perfect. So I'd just like to address some of these insights that you have. First of all, ISM in general, when it was first put together, right, was in a very low computer resourced situation and a very low network situation. So you brought all the people together so they could communicate in one room in very high quality. So your idea of what happens outside the room is that really you need to have people actually communicating somehow, okay? And so the original methods and so forth were put together in a non-networked world. Everything's networked now. So depending upon how you want to communicate with people, there might be some ways to do that. The other point, and I think this is more along the idea of ontologies and ontology development that's being discussed right now on the ontology list, is how formal is an ontology. So have an ontology that everybody in industry X, this is the oil and gas industry ontology, this is the medical industry ontology, this is the XYZ ontology, okay? So everybody agrees to that, but what happens if something new comes along? So I come up with something new, and now really in systems engineering and in structural modeling, you're looking at new and unknown things, right? So, okay. And what they're saying on the ontology group is this is where the ontology within the group changes really fast, because you're developing and coming to consensus of how these things fit. And so depending upon the people in the room, if they're all doctors, or if they're all oil and gas execs, or if they're all government officials, they all have a standard set of ontologies that they already know about, right? So They have something new that they have to work with, and then they have to take that and then fit it into their existing ontologies. And so in my case, I think another way to ask a question about how does this become standardized is more or less how do these things, how are they conceived and put together so that they can integrate with things that are already standardized. So when the integration is going to change what's there now, but this won't completely replace, it will just integrate. And you need that constant ongoing integration. And now the final comment, when they first started with the piece there on the with ISM and structural modeling, they just viewed it as events. Oh, we'll have this event, this event, this event. But when they implemented it in Mexico at the president's level, right, it was a continuous operation. And I believe they also did that at the FDA. Kevin can talk about that. Instead of having an event, you have this capability. You now have an integrative type of capability that's always available. And so the idea that when you say what happens to people outside the room, that kind of concept goes away when you think about, oh, I have an ongoing resource capability of integrating folks at this level of precision. Okay, so we got about another 10 minutes.
Joe?
Yes.
Jack Ring, I want to emphasize this point you just made because I think it's very important. Ontology is one thing. It's a set of knowledge claims about what exists, but the ramifications of how those things influence one another is not revealed by an ontology. It is revealed by the ISM process in which a group of people individually answer a question. And that really brings them into dialogue so that they begin to understand one another's meanings and understand why they're different. So the ISM process is a key point here.
I agree, Jack. I agree.
And so just by reading these papers, you will not discover how to bring a group into a coherent knowledge base. Not until you understand the ISM process and, in fact, experience it, will you understand how to bring people together in a more coherent dialogue. Thank you.
Yeah, couldn't agree more. But there's different views, and I'm really hoping that we'll be able to start doing that soon. Any other comments?
Yeah, so I had to leave for a while. The streamer had froze up for some reason. So I'm not sure about that yet. It's a matter of, we're currently at Judith Rosen's house visiting in New York, upstate New York, and she wanted to say hi to people. Let's see, the other thing was, yeah.
Hi, Judith.
Good. So the ontology, I guess one question is, ideally, in doing all of this work, there's the question of what's ideally desirable and what's feasible with different kinds of trade-offs. I think the important thing is if you want to leverage technology, you need to make compromises and you need to get things into standardized mathematical logical form. The question is how you mitigate the compromises that you need to make in order to do that. So the computing, the ontologies that we're talking about are computer ontologies. They're ontologies as codified for, as Jack says, knowledge claims codified for computers about what exists. That's pretty sparse. it can't capture everything that is needed for coherent knowledge use. So there's as Kevin often points out, and I hadn't realized a lot of the trade-offs when he talks about actual use of ISM and how people get tired and it costs money, and there are these real world limitations that have to be figured in that keep you away from the ideal group modeling picture. That's my impression there. Interesting.
Yeah, there's I think basically I put the intro back up again, and I think to me the key point is that what we're doing is if we're going to design this object language, and we're not going to design the natural language, but we're going to design the object language. Some of the criteria are to minimize resource consumption and maximize knowledge and value creation. And so this is where in the design of the logic, we can have an impact on these two criteria. And those are the types of things that I believe are important. Just kind of getting down to the end of this, one of the things that Mary and I noticed when we did the evaluation of the existing DOS software and developed the proof of concept or validated the material out of the appendix of 2 of the Handbook of Interactive Management, is we then tried to start use that software to validate other published sessions, and we couldn't do that. And one of the things that became obvious, and we wrote a couple other papers on this, was the fact that the logical relationships that were supported apparently by the DOS software had to be a strict order in the way it was applied. But what we said was, well, you don't really need to do that because you have the people there. It doesn't matter. The people are the source of the information. How are they participating? These folks are going to be your empirical knowledge. And so instead of saying is A relationship to B, right? To do that and to logically infer, you need to have a strict order. But if you don't have a strict order, then you can just ask the group, you can just say, what has a relationship to A? What has a relationship to B? And the people, they can give you a list. Yeah, this, and this. And you don't have to logically infer that at all. You just ask the people because they're there. And so now we have 2 types of logical situations. We have one where you can use, if it's a strict order relationship, you can really minimize resources. If it's not a strict order relationship, you can still ask the same question and minimize computing resources because you're relying on the humans and their knowledge in the group to fill that in. You're not trying to infer it. And so these are types of activities and the types of functions that structural modeling will add to the classical ISM, which I believe will make it much more valuable.
I take exception.
Okay, good.
Let us say that there are 10 items that we have to deal with. And
Yeah.
so there are 100 possible relationships between those 10 items. And
Right.
we have 10 people. So we ask each person to nominate as many relationships as they want between those 100 things.
Yeah.
And you're going to end up with about 10,000 assertions, and you'll never finish. I have watched this happen, and the people get up and leave in the middle of the operation.
And isn't it the point of system science to try and pin down the ones that recur, so that we don't need to reinvent the wheel every time? Not saying that not having people reinvent the wheel, I mean, it may be good to have people to reinvent the wheel because then they own the process of learning, but
Yes.
Yeah, that's the question that I have. How do you actually, because ontologies pin down all kinds of things, but they don't pin down processes, or they don't pin down recurring patterns of systems.
But when you look at the ISM process, the question is, what is there a significant relationship between A and B? And if you have 10 people in the room and 8 of them or 7 of them say yes, then you take that as your starting point. If only 2 of them say yes, you go ask a different question, because the ISM process is designed to let you focus on the most important relationships first, and then come along afterwards and resolve any clutter.
Yeah.
The shortcoming in the ISM process, which we have experienced, is we use Bayesian belief network on top of it, so that when we ask people, is there a significant relationship, we ask a second question: what is your authority or knowledge level for making the claim you just made? And they could score that from a 1 to a 10, which 10 means they believe they're an expert. And so when we then take the responses of ISM through a belief reduction, we get a much different pattern and a much more believable. The people are believe it much more than the straightaway ISM. And
Yeah.
I brought this to Warfield's attention right before he passed away, and bless his heart, he didn't say no.
Well, yeah, I think that there's many advances, and I think there's many things that you can look at that are useful when that can be added to the core approach. And
Yes.
what you're talking about is the real world application of asking people for multiple answers, right? The
Yes.
real world response. Now, as opposed to the theoretical response. So I could write a test system, I could write the logic, I could test it, and I could do the multiple response thing, and I could have random answers, I could do all kinds of things, and I'm still going to get a repeatable answer. When I go and I ask people, right, there could be big arguments. There could be all kinds of disagreement, right? But
Yep.
but that doesn't invalidate the mechanism. So the idea would be, can we take this mechanism and improve this somehow?
Well, be careful, because you can in fact get them to agree, but they can agree on the wrong answer.
Always.
Well, so
I mean,
you
that's
have to
always
have
step one, isn't it?
you have to have a guard in there that prevents group think.
Oh yeah, no, I understand. So I think this has been very valuable. I would like to continue. Anyone that wants to kind of work on developing these requirements and putting these ideas together, just let us know on email, and I'll basically start a document, or however people want to work together to do that, because I would really like to start refining. Well, I'd like to do 2 things. One, find people that like to work with the existing Warfield Windows-based software and test that out, run it through its tests. And then 2, start refining and requirements for an updated web-based software.
Well, although I make comments, I want to emphasize that I think you and Mary are doing some wonderful work, and I'm not in any way trying to diminish it. I'm just simply suggesting that there are some things that we need to think about on the human side of the equation as well as the logic side.
I agree with you, Jack. You're
good. And Janet, by the way, probably can contribute more in that dimension than I can, certainly.
Well, so we're getting down to the end of the hour here, and anyone that would like to participate in any way, just send an email out, and we'll. So what about see, this is the 7th, so the 21st, right? Anyone want to take the topic for the 21st of December? Yes, no, everybody holidaying?
I'll be on the road that day, unfortunately.
Okay. Well, shall we cancel that day? Is everybody going to be busy, or should we just have a continuation of this requirements development? What does the group think? How would you like to do?
I've been elected Santa Claus and driving 12 Mercedes, so I can't do that.
Okay. It looks like we're going to do, looks like we'll skip the 21st and shoot for the 1st of January. Let's see, what is that going to be? What date will that be in January? That will be January, come on, next year is November. So that will be January 4th, it looks like. January 4th, when I'll get some material together, and hopefully we'll have a version 2.0 of the Ontology as a system paper out with a little more specific details and more details on the implementation.
Sounds good.
Okay, take care. Have a good holiday, folks.
Thank you. Bye-bye.